Hey, what's up YouTube? My name is Abhishek, and in this video I want to explain you guys how the electromagnetism and relativity are interconnected with each other so that no laws of physics are broken. So basically what happens is that the electric and magnetic forces do act different because of the relativistic phenomena or the change in the frame of reference. This usually happens because of length contraction, because of which you observe a different electric and magnetic field in charge if you observe that same charge or a moving charge from a different frame of reference. So the charge can be moving or cannot be moving for you. And that is how the electromagnetic forces change for both the observers. So let's see how.
Let's say an observer called Ted here is watching this rod in free space. The rod has a linear charge density lambda, and the charges inside the rod are static for Ted. So what Ted sees here are only electric fields, and the length of the rod he sees is L. Now for another observer, John, who is moving at a speed of 1,000,000 meters per second, sees the same thing, but with a different parameters. So he sees the same rod, but with a contracted length of L prime. And because of that, the linear charge density also changes for John here. Well, why does the linear charge density change? That's because the Einstein's postulate says that the amount of charge inside this rod is similar for both Ted and John, but length changes. And that's why the linear charge density also changes, which is nothing but the charge per unit length.
So if you're confused about the length contraction, what it basically says is if you have one frame of reference S, which is at rest, you're going to observe a random rod or any length with some length L. But if other frame of reference watches that same object, which is not at rest with respect to the frame of reference in rest, then this frame of reference, that is every object or every conscious in this frame of reference is gonna measure the length of the rod as L prime, which is always going to be less than the actual length because of the length contraction method, where your L prime is going to be the actual length, which is the rest length, divided by gamma, where gamma is a factor which is equal to 1 over square root of 1 minus v square over c square. So now you may get it. When a frame of reference is moving at a velocity v, then the gamma comes into play, where you can just plug in the value of v and see how much the length has been contracted for this moving object. So back to my animation. This was our frame of reference. So this is my frame of reference, which is at rest. So my velocity is equal to 0. I see this rod, a charged rod this time, with let's say net charge q enclosed in it. Let me change the marker. And now, other frame of reference, which is not at rest, let's say at a velocity v in the rocket, he sees this charged rod with a different length according to the length contraction which I just explained, L prime, which is original length over gamma, where gamma is the operator. So what's the similar thing that both of these frame of reference notice about this rod? This is the electrostatic electrostatic force applied by this rod and the amount of charge enclosed in it. So if the charge is q, then for this frame of reference, the charge is also going to be q. There are not extra charges created or destroyed because of the change in the frame of references. So if the charge is q, but the length is different, then charge per unit length, which is lambda, sorry about gamma again, lambda, which is our charge per unit length, for this frame of reference, which is at rest, is going to be lambda q by L. But for the frame of reference which is in motion, the length has been changed. So the lambda will also change, which will be q over L prime. That is the length for this frame, which is L over gamma. So my lambda would be q by L, which is our original lambda. This is lambda prime for this frame, is equal to lambda times gamma. And this is a very important conclusion for electrodynamics when we try to bring in the frame of references. the linear charge density or any charge density of any object doesn't remain the same when we change the frame of reference from rest to some velocity v. It usually shows significant effects when you have velocity which is almost greater than or equal to 10% of the speed of light. So when you have attained a very high velocity, more than 1,000,000 meters per second, you're going to notice that change, that significant change in length. For example, a 10-meter rod would be 5 meters for you at some velocity, let's say 0.8, that is 80% of the speed of light. So similarly, for this rod, my length is going to be contracted, and that's why my linear charge density is going to increase, because my new linear charge density in this frame of reference is equal to lambda gamma, which is 1 over square root of 1 minus v squared upon c squared, is going to be lambda prime is lambda over square root of 1 minus v squared over c squared, where velocity can be, where v is the frame of reference velocity for s prime. So you see the lambda value increases because this value is always going to be less than 1. So our lambda value is going to increase as we increase the velocity. So for any rod, we can increase the linear charge density or the charges inside the rod per unit length if we increase our velocity more in more practical ways closer to the speed of light. So from Gauss's law, I can conclude that at a certain distance r from both these rods, well, the same rods but from different frame of references, by Gauss's law I can say that E times the area is Q enclosed over the permittivity. And for this rod, I can also say that E times area of this rod, according to S prime, equals to Q enclosed, which is going to be similar for both. Remember, charges will only appear denser for S prime over epsilon naught. So again, let's try to calculate the area of this rod, which is 2 pi r times the length of the rod, L. And now, for this other rod, according to the S prime, same rod, according to the S prime frame of reference, I can say that the area is 2 pi, same distance from this rod r, times L prime, the contracted length. Let me just box this thing. So again, I'm plugging the values of area. So let's calculate for S first. E will be equal to Q. And I'm just taking the area down, which is, to understand better, I will write Q over L over 2 pi epsilon naught times R, which is, we have our Q over L as lambda. So I can also write electric field as lambda over 2 pi epsilon naught times R. So this is our electric field for S frame of reference. But for this frame of reference, we get a different area. We have area as the function of L prime, which is the contracted length. So our E will be equal to Q over L prime this time over 2 pi epsilon naught times the same distance R. So I can write Q over L prime as the new or the increased charge density for this contracted rod, which will be lambda prime over 2 pi epsilon naught times R, which is my electric field for, which is my E prime, my electric field for the S prime frame of reference. I hope you understand, like when I try to increase the velocity of this object or my velocity, that is if I'm moving and the charge is moving backwards relative to me if I'm in the rocket, then the charge is going to appear more contracted, the charges inside this rod are going to appear more dense, and the electric field that I am going to calculate from this rod that is moving back for me. I'm in the rocket again. So this rod is moving back for me, and the electric field for me for this rod would be lambda prime over 2 pi epsilon naught r. But for S frame of reference, some person who is at rest, he will see the rod at rest, and so he will calculate, no, he'll say no, the electric field is lambda over 2 pi epsilon naught r. So I have, let's say 4 coulombs per meter. So I have 4 coulombs per meter over 2 pi epsilon naught times the radius. But this person will say, no, I have 8 coulombs per meter over 2 pi epsilon naught r, the distance, my reference. Alright, so what have we learned till now is that when we have a frame of reference which is at rest, it's going to observe the rod of length L with electric field E bar, let's say, which I just derived. But for the other frame of reference moving at velocity v, is going to observe the length L prime with electric field which is E bar, the rest electric field, times gamma. Or I can also write E bar over square root of 1 minus v square over c square. So v is the velocity of this frame of reference, and the electric field, and this value is always going to be less than 1. So for a moving particle or a moving object which has a velocity, very high velocity, velocity close to the speed of light, let's say, it's going to observe electric field for the same rod in a much higher magnitude, depends on this operator, than the electric field that has been measured by the frame of reference which is at rest. Do you understand me? Okay, so what we know by far is that in S frame of reference, electric field is equal to lambda over 2 pi epsilon times r, and in S prime frame of reference, our electric field will be lambda prime over 2 pi epsilon naught r. Let me also acknowledge the fact now that when we have a moving charged body, the charge also produces magnetic fields. Well, let's see. In our frame of reference here, let's say I'm in a rocket now, but I'm rest in my own frame of reference. So the charge is moving for me in a backwards direction of v. And let's say that's why the charges inside the rod are also moving. And by the right hand rule, I can say that if the charges are moving in the negative x direction, I have the magnetic field going in the clockwise direction. That means I'm going to have a magnetic field in the negative k cap direction, which will be my direction of the magnetic field. So, for me, the rod is moving backwards. That means the charges are producing magnetic fields, first of all. So I can calculate the total current here. Let me draw here in the rocket first. I'm seeing this charge moving, and I'm at rest for myself. But the charge is moving backwards at a velocity v. So my current will be the change in charge over change in time, which I can also write as change in charge over change in length, times change in length over change in time, where this thing becomes lambda prime. Let's call this I prime because we're measuring in the S prime frame of reference. And this will be lambda prime, and this part will be dx over dt. This will be velocity of this charge. So I can write current as lambda prime times v, where you know what lambda prime is. So now I can apply Ampere's law here to make that basically says that the magnetic field will be equal to mu naught times the current over 2 pi times the distance. Well, let me rub this thing real quick to write down what it actually says. So mu naught times the current lambda prime times v over 2 pi times r. The r, which is the distance from a rod, which will be same for both the frame of references. But I can also write the electric field as lambda prime over 2 pi epsilon naught r. So lambda prime over, if I multiply and divide this thing by epsilon naught, I can separate the value of lambda prime over 2 pi epsilon naught r as nothing but the electric field. So this is my electric field. So I can write the magnetic field as equal to the electric field prime, let me be precise, electric field prime in the S prime direction times mu naught epsilon naught times V. So this is a very important conclusion that we get. The magnetic field in the S prime, so for me, if I'm moving in a rocket, the magnetic field at the point R will be the electric field times mu naught epsilon naught times the velocity that the charge is traveling for me. And the direction of magnetic field will be negative k cap direction. Alright, so now we know the magnetic field, now we know the electric field, but I can also write this electric field as the function of the rest frame of reference electric field. That is, according to this charge, if the charge is at rest for itself, that means the charge, or anyone that is standing on this charge, I won't guess how, but he or she would see the electric field as E, which is lambda over 2 pi epsilon times R, which is nothing but E prime times gamma, which we just discussed. So I can write E as E prime times gamma. So my magnetic field prime at the S prime frame of reference will be equal to the E prime, which is E times gamma. Well, it should be E times gamma, not E prime times gamma. Oh wait, hold on. So this is my electric field. So this is E prime, which will be equal to E times gamma. I'm sorry about the confusion. So B bar would be equal to E prime, which is just the normal electric field, times mu naught epsilon naught times the velocity over square root of into gamma. So it will be 1 over square root of 1 minus V square over C square. So this is what we learn now, where the magnetic field here is E bar, which is the rest electric field, times mu naught epsilon naught times V over square root of 1 minus V square over C square. Well, I can try to simplify this formula for you. I know that the velocity of light is equal to 1 over square root of mu naught times epsilon naught. So I can just write mu naught times epsilon naught as 1 over C square. So I can write B bar is E. So the magnetic field, that is the magnetic field in S prime frame of reference, is the electric field in S frame of reference times the velocity over C square times 1 minus V square upon C square. The whole denominator is a constant. And this is what we get as the magnetic field. Now let's get to a simple question or a simple dilemma that we go through when both the observers, let's say here is another observer at rest, and this is me, of course. Both the observers see the same thing, but something different happens.
So our friend Ted here watches this charge moving in the positive x direction, and the charge deflects towards Ted or towards us because of the present magnetic field in the negative y direction, as you can see. So Ted observes that the charge is negative and the magnetic fields have deflected the charges. But for another observer, John, who is this time moving at the speed of the charge, he observes Ted moving backwards, but the charge is at rest. But because of the present magnetic field in the rest, the charge still deflects towards John and Ted and us at the same time. Well, how did this phenomenon occur if there was no magnetic field for John here?
So what I was trying to say here is that the electric and the magnetic fields try to act like the close blood brothers, if that's a good reference, and contribute to each other's forces towards the particle so that no laws of physics are broken. Let me explain more intuitively. So again, you have an S frame of reference which is at rest, and for S frame of reference, a charged particle with net negative charge, let's say, is moving in with a velocity v in the x direction. So what's going to happen is that this is a negative charge, and if we apply a magnetic field, let's say outside the board, then my magnetic force will be Q times V bar cross B bar, where Q is our electrons that are inside this charged particle. So the magnetic field will be in negative j hat direction. And so this particle will, or these particles will deflect in negative y axes. Now let's see what, here the magnetic fields are playing the role. But let's see what happens when we change our frame of reference to S prime. You may have guessed by now. Now for S prime, the only motion that has been offered by this particle is the motion in the negative y direction. And also this negative y direction motion is because of the magnetic field in the S prime, in the S frame of reference. The S says that S frame of reference says there is a magnetic field which is outside the board, and that's why the object is deflecting downwards. What S prime will say is that there is actually no magnetic field. Well, why is there no magnetic field? Because both have same velocity, and that's why both are at rest. Both have zero relative velocity. So S prime will say that there is no magnetic field. But what S prime will say is that there is an electric field E bar acting on this particle, which is also in negative j hat direction. So try to think about it. In S frame of reference, the rod is moving, and that's why the magnetic fields are playing in to deflect the rod to the negative j hat direction. But in the S prime frame of reference, the same rod is getting deflected downwards, not in front because the velocity is zero, the relative velocity is zero. But the charges are deflecting downwards, but this time because of the electric field. So S frame, S prime, or if I say S double prime, where the similar rod is, let's say, moving at a charge, let's say, parabolically downwards. So here I can say that there is also non-zero magnetic field because the relative velocity is not zero, and that is why the charges are moving downwards parabolically. Now the formulas of the electric and magnetic field you can easily derive the way I did, but this is how the charges interact when you try to change the frame of references with respect to the observers. Of course, this doesn't have to end here, because in the future, if you go explore the topic, you will find something called as the electromagnetic tensor, which will look like this. I won't go about tensors in this video, but all I will say is that tensors usually represent the interaction of the particles or any interaction of the vectors as per the change in the coordinates. So this is a rank 2 tensor, is the electromagnetic tensor, and it has dimensions as 4. So it's a 4-dimensional rank 2 tensor. So it says the interaction of the electric and magnetic fields with respect to the x, y, z direction, where the mu represents x, y, and z, and also the time dimension. So in the space-time fabric, how these particles change, how these particles interact, and how is the motion of this particle going to take place. This is represented by the electromagnetic tensor. But that's a story of a different video. For now, I'm really hoping, and I would be delighted if you guys try to establish that link between the electrodynamics and electromagnetism and how the motion of the charged particles vary with respect to the frames of references. Because again, my last point would be the electric and magnetic fields are not the same for two different frame of references. If someone is moving at a different velocity, he or she is going to notice a different electric and magnetic field on that charged particle. And someone who is at rest is gonna observe something different. So that is it for this video. If there's any part of this video that you may not have understood correctly, please let me know in the comments. And if you did understand everything correctly, still let me know in the comments. And do like and subscribe to keep me motivated to upload more content online. And finally, thank you for watching.